design a medical exam room minimizing electromagnetic fields, begin with the room design itself. Firstly, consider electromagnetic field shielding. Install a Faraday cage around the entire room. This can consist of a conductive metal mesh or fabric that effectively blocks electromagnetic fields. Secondly, use metal-lined windows and doors. This will prevent electromagnetic interference from outside sources. Thirdly, address grounding. Ensure proper grounding of all electrical equipment. This minimizes stray currents. Install a dedicated grounding rod specifically for the exam room. Fourthly, examine lighting. Use light-emitting diode or fiber optic lighting fixtures. These emit minimal electromagnetic fields. Avoid fluorescent and incandescent lighting. Fifthly, consider the receptacles. Use shielded receptacles with grounded plugs. Minimize the number of receptacles in the room. Sixthly, provide adequate natural or mechanical ventilation. This reduces the buildup of static electricity. Now let's discuss the equipment needed. An electromagnetic field meter is essential. Use this device to measure electromagnetic field levels in the room. Ensure they are within acceptable limits. Equip the exam table with a conductive mattress and pillows. This dissipates static electricity from the patient. Install conductive curtains around the exam area. This minimizes electromagnetic interference from surrounding areas. Consider an ionizing air purifier. This reduces static electricity in the room. There are also additional considerations. Ensure the room is comfortable and welcoming for patients, despite the electromagnetic shielding measures. Be aware that electromagnetic field shielding can be expensive to implement. Consider consulting with an electromagnetic field specialist. This provides professional guidance and design optimization. Establish a regular maintenance schedule for testing and maintaining the electromagnetic field shielding and equipment. Proper grounding is critical for safety and electromagnetic field reduction. All electrical equipment within the exam room should be connected to a common ground point. This helps to minimize the potential for stray currents and voltage differences, which can contribute to electromagnetic field generation. The grounding system should comply with all applicable electrical codes and standards. This usually means adhering to the National Electrical Code or similar regulations. A dedicated grounding rod driven into the earth provides a low impedance path for fault currents to return to the source. This is in addition to the regular grounding conductor that is run with the electrical wiring. The grounding rod should be made of a conductive material such as copper or copper-clad steel. It should be installed according to the manufacturer's instructions and local electrical codes. Shielded cables and conduits can further reduce electromagnetic field emissions from electrical wiring. These cables have a conductive layer that surrounds the conductors and is connected to ground. This shields the surrounding environment from electromagnetic fields generated by the current flowing through the wires. Metal conduit provides similar shielding benefits. When installing shielded cables and conduits, ensure that all connections are properly made and grounded. Any gaps or discontinuities in the shielding can compromise its effectiveness. Select electrical equipment with low electromagnetic field emissions. Many manufacturers now offer equipment that is designed to minimize electromagnetic field generation. Look for equipment that meets recognized standards for electromagnetic field emissions, such as those established by the Institute of Electrical and Electronics Engineers or the International Electrotechnical Commission. When selecting lighting fixtures, opt for light-emitting diode or fiber optic options. These technologies produce significantly lower electromagnetic fields compared to traditional fluorescent or incandescent lights. Light-emitting diode fixtures are also more energy efficient and have a longer lifespan, which can help to reduce operating costs. Fiber optic lighting uses optical fibers to transmit light from a remote source. This eliminates the need for electrical wiring within the exam room itself, further reducing electromagnetic field exposure. Minimize the use of wireless devices in the exam room. Wireless devices such as cell phones, tablets, and wireless medical equipment emit electromagnetic radiation. While the levels may be relatively low, they can still contribute to the overall electromagnetic field environment. If possible, use wired connections for data and communication. If wireless devices are necessary, keep them as far away from patients as possible. Regularly measure electromagnetic field levels in the exam room. This helps to ensure that the shielding and other mitigation measures are working effectively. Use a calibrated electromagnetic field meter to measure electromagnetic field levels at various locations within the room, especially near electrical equipment and wiring. Compare the measurements to establish safety standards and guidelines. If electromagnetic field levels exceed acceptable limits, take corrective action to identify and address the source of the emissions. This may involve improving shielding, rerouting wiring, or replacing equipment. The Faraday cage should be constructed of a highly conductive material such as copper or aluminum. The mesh size or hole size in the cage should be small enough to effectively block the frequencies of electromagnetic radiation that are of concern. The cage should be fully enclosed with no gaps or openings. All seams and joints should be properly sealed to maintain continuous conductivity. The effectiveness of a Faraday cage depends on the frequency of the electromagnetic radiation being shielded. Higher frequencies require smaller mesh sizes. Consult with an electromagnetic field specialist to determine the appropriate mesh size for the specific application. Metal-lined windows and doors are essential for preventing electromagnetic interference from entering or leaving the exam room. The metal lining should be continuous and well grounded. The glass in the windows should also be coated with a conductive film to block electromagnetic radiation. Doors should have conductive gaskets around the perimeter to ensure a tight seal when closed. Ventilation is important for maintaining air quality and preventing the buildup of static electricity. However, ventilation systems can also introduce electromagnetic interference if not properly designed and installed. Use metal ductwork that is grounded to shield against electromagnetic radiation. Install filters to remove airborne particles that can contribute to static electricity. Consider using a dedicated ventilation system for the exam room to isolate it from other areas of the building. Static electricity can build up on surfaces and equipment in the exam room, creating electromagnetic fields. Use anti-static materials for flooring, furniture, and equipment. Apply anti-static sprays to surfaces to reduce static charge buildup. Install grounding straps on equipment to dissipate static electricity. The conductive mattress and pillows should be made of materials that are both comfortable and conductive. Carbon fiber fabrics and metallized textiles are common choices. The mattress and pillows should be connected to ground to dissipate static electricity from the patient's body. The conductive curtain should be made of a material that is effective at blocking electromagnetic radiation. Metallized fabrics and conductive meshes are commonly used. The curtains should be installed so that they fully enclose the exam area, creating a shielded space around the patient. An ionizing air purifier can help to reduce static electricity by neutralizing charged particles in the air. These devices use high voltage to create ions that attach to airborne particles, causing them to clump together and fall out of the air. Select an ionizing air purifier that is designed for use in sensitive environments such as medical facilities. Consult with an electromagnetic field specialist to determine the best approach for shielding the exam room. A specialist can perform a site survey to assess the existing electromagnetic field environment. They can also provide recommendations for shielding materials, grounding techniques, and equipment selection. A specialist can also help to design and install the shielding system and verify its effectiveness. Regular maintenance is essential for ensuring that the shielding system continues to function properly. Inspect the Faraday cage, metal-lined windows and doors, and grounding system regularly for any signs of damage or corrosion. Test the electromagnetic field levels in the room periodically to verify that the shielding is still effective. Repair any damage or replace any worn components promptly. Keep accurate records of all maintenance activities. Proper training is essential for ensuring that staff understand the importance of electromagnetic field shielding and how to operate the equipment in the exam room. Provide training on the proper use of the electromagnetic field meter, anti-static materials, and other shielding measures. Emphasize the importance of following all safety procedures. Ensure that staff are aware of the potential sources of electromagnetic interference in the exam room. Ongoing monitoring of electromagnetic field levels in the exam room is crucial to ensure the continued effectiveness of the shielding measures. Regularly use a calibrated electromagnetic field meter to measure electromagnetic field levels at various locations within the room, especially near electrical equipment and wiring. Compare the measurements to establish safety standards and guidelines. If electromagnetic field levels exceed acceptable limits, take immediate corrective action to identify and address the source of the emissions. The design should comply with relevant regulations and standards, including those related to electrical safety, electromagnetic compatibility, and medical device safety. Consult with relevant regulatory agencies and standards organizations to ensure compliance. Keep up to date with the latest regulations and standards. Document all aspects of the electromagnetic field shielding design, including the materials used, the installation procedures, and the test results. This documentation will be helpful for maintenance, troubleshooting, and future upgrades. The design should be flexible enough to accommodate future changes in technology and equipment. Allow for the possibility of adding or modifying shielding measures as needed. Use modular shielding components that can be easily reconfigured. The design should consider the potential impact of the shielding measures on other aspects of the building, such as ventilation, lighting, and fire safety. Coordinate the design with other building systems. The design should minimize the risk of electromagnetic interference with other medical equipment in the building. Locate the exam room away from sensitive equipment. Use shielded cables and conduits for all electrical wiring. The design should consider the potential impact of electromagnetic fields on patients with implanted medical devices such as pacemakers and defibrillators. Consult with a cardiologist or other specialist to determine the appropriate shielding measures. The design should consider the potential impact of electromagnetic fields on pregnant women and children. Use shielding measures to minimize their exposure to electromagnetic radiation. The design should consider the potential impact of electromagnetic fields on staff who work in the exam room. Provide training on how to minimize their exposure to electromagnetic radiation. The design should be aesthetically pleasing and create a comfortable and welcoming environment for patients. Use colors, textures, and lighting to create a calming atmosphere. The design should be cost-effective and balance the need for electromagnetic field shielding with other budgetary considerations. Explore different shielding options and select the most cost-effective solution. The design should be sustainable and minimize the environmental impact of the shielding measures. Use environmentally friendly materials. The design should be resilient and able to withstand natural disasters and other disruptions. Use robust shielding materials that can withstand physical damage. The design should be accessible to people with disabilities. Provide adequate space for wheelchairs and other assistive devices. The design should be secure and protect patient privacy. Use shielded windows and doors to prevent eavesdropping. The design should be easy to clean and maintain. Use smooth, non-porous surfaces that can be easily disinfected. The design should be adaptable to different types of medical exams. Provide flexibility in the layout of the exam room to accommodate different procedures. The design should be future-proof and able to accommodate new technologies and equipment. Allow for the possibility of upgrading the shielding system in the future. The design should be well documented and easy to understand. Provide clear and concise drawings and specifications. The design should be reviewed and approved by qualified professionals. Obtain input from engineers, architects, and medical professionals. The design should be implemented by qualified contractors. Use experienced contractors who are familiar with electromagnetic field shielding techniques. The design should be tested and verified after installation. Use a calibrated electromagnetic field meter to verify that the shielding is effective. The design should be monitored and maintained on an ongoing basis. Regularly inspect the shielding system and test the electromagnetic field levels. The design should be continuously improved based on feedback and experience. Implement changes to the design as needed to improve its effectiveness. The process involves firstly understanding the electromagnetic environment. Secondly, setting achievable goals. Thirdly, using appropriate shielding techniques. Fourthly, grounding and bonding. Fifthly, filtering. Sixthly, cable management. Seventhly, regular inspections. Eighthly, documentation and updates. Ninthly, training personnel. Lastly, continuously improving the design.